This is the solution video for question 18 from section B of the 4th sample test for CSAT. In this question, we're told we have a poll with two choices, and we run it with n participants where n is greater than 2. And we're told each participant chooses at random one of the options. And we're told the poll then shows, when it's finished, the results as percentages to the nearest integer, i.e. x rounded takes the value of the floor of x plus 0.5, where your floor function outputs the greatest integer less than or equal to y. This is essentially a very formal way of saying we round halves up. When then asked what is the probability that the sum of the two shown percentages, once we've finished our poll, is not 100. So, firstly, let's introduce a little bit of notation. We've got options A and B, with A and B, the number of choices for A and number of choices for B, respectively. Now, what do we want? We want ones rounded to sum, not to 100. So you can probably tell, the only way that's going to happen is if A and B as percentages are something 0.5. So, how does this occur? Well, we want 100 times A over N, so percentage A is to equal to something 0.5. So i.e. we want it to be equal to some odd number over 200. So we'd say something like 2k plus 1 over 200 for varying k. And with a little bit of rearrangement, so timesing by n and dividing by 100 on both sides with this 2k plus n, 2k plus 1 over 100, over 2, we obtain that A must be equal to 2k plus 1 over 200n for some k between 0 and 99, because that varies this between 1 and 199. So we've got A here, and we're looking at the sum from k equals 0 to 99, the probability that A is 2k plus 1 over 200 times n. And A will be a binomial distribution, because we need to pick A times from n total trails, and each one's a half. And we know binomial distributions only generate integers as answers. So we know most of these will be 0, because this isn't always an integer. So the real question we have to ask is, when is this thing an integer for differing n and k? Once we work that out, we can work out what our non-zero terms are in this sum for different n and k, sub in the formula for the probability for a binomial, and we'll get an answer. So now let's address our question of for which k 2k plus 1 over 200n is an integer. So we're going to rewrite it like that, because this answer is clearly going to depend on things that divide n. So to write the denominator out in prime factors is just going to help us a little bit. So the first thing we notice is 2k plus 1 for any k is going to be odd. So if n isn't divisible by a, i.e. 2 cubed, we've got no chance of this being an integer. So if 8 doesn't divide n, this means, then this thing is never an integer. So now, suppose that 8 does actually divide n, so we can write n equals 8n. So if we write that, then this simplifies to this, because the 2 cubed and the 8 cancel. And now let's look at this. So let's look at a nice case first. So let's suppose m is a multiple of 25. Well, that's the same as 25 dividing m is the same as 25 dividing n, because timesing by 2 cubes shouldn't make any difference to that divisibility by 25, because 2 and 5 are prime numbers that are different. And so we know if this is the case, then m over 5 squared will be an integer, and 2k plus 1 is certainly an integer, so this means it'll always be an integer for any k. Now let's look at the other cases. So if 5 divides m, but 25 doesn't divide m. So then, m over 5 squared, we know we've got one 5 in here, but we need another 5 from here to make this an integer. So this is an integer if and only if 5 divides 2k plus 1, or 2k plus 1 is a multiple of 5. And our final case, if 5 doesn't divide m, so remember this is equivalent to 5, we can basically substitute in m and n anywhere here, because divisibility isn't affected. Divisibility by 5 and 5 squared isn't effective when we're just timesing by 2, 4 or 8. So if 5 doesn't divide m, we see that we need 2k plus 1 to be a multiple of 25. So 25 to divide 2k plus 1. So now we've got a complete picture for different values of n, what k makes this an integer. So now we've determined for what k and n we have integers here. And remembering the fact that a is binomially distributed with parameters n and a half, we can just work out what these probabilities are. But we have to do it case by case. So the easy case, 0 with 8 doesn't divide n. So if n isn't a multiple of 8, what we determined was that this thing is never an integer, and the probability a is not an integer is 0, so we're just summing up zeros, and we have 0. So now let's go to our next case. So 25 divides n and 8 divides n. So that's the same as 200 dividing n. And in that case, we can just sum up all these probabilities, and this is always non-zero, because this thing is always an integer. So we just sum these up, and once we substitute our formula in afterwards, we'll be done. Next case, 8 divides n, 5 divides n, and 25 doesn't divide n. There's a few different ways you could express this information, but essentially in this second case here. And what do we need here? Well, we need, for this thing to be an integer, we need 5 to divide 2k plus 1. And 2k plus 1, 5 dividing it means we can have 5 here, 15, 25, because we can't get to 10 or 20 or 30 because this is only odd. So 5, 15, 25, 35, etc. So we can express that from m equals 1 to 20, 10m minus 5, that should pick up all the multiples of 5 that aren't multiples of 10 between 0 and 200. And we do similarly for our last case. So 5 doesn't divide n, but 8 divides n. Then we need 2k plus 1 to be a multiple of 25. Clearly, the only ones we can get to are 25, 75, 125 and 175, because we've got no hope of getting to even numbers. And so we've just got to sum over m equals 1 to 4, 50m minus 25 over 200 times n. And these will be all non-zero terms we've written here. So now if we just use this binomial, the fact that a is binomial, and sum in the formula, we should be done. So using the fact that a is binomially distributed, we know that these are our answers directly subbing in what the probabilities are from a binomial distribution, and we have these answers as required.